I have a question.
What's the question?
Is this your first time speaking at DEF CON?
It is.
Oh, excellent. So actually, I wanted to say that we were experimenting with something new this year at DEF CON. Yeah, could you set us up, please? We were looking for a drone delivery system.
What is that? What is this?
What do you think? Will that deliver shots?
That's cool.
You all know how this works. You've been here long enough.
Okay.
Wait, slow down there, man. Whoa. Well, all right.
Cheers. Thank you.
Cheers. And now back to our regularly scheduled talk.
Okay. So, now I feel a bit warmer. Okay. So I was saying, let's see how the usual exploitation process takes place. So if you're an exploiter, you're trying to exploit something, usually first of all you have to find a vulnerability. And this vulnerability has to be useful. And by useful means, I mean that you have to be able to basically divert the control flow of the program to some address you want. And once you're able to do this, then you can perform your desired actions, like, I don't know, invoking the system library function and execv, or launching program, copying wallets. I mean, doing the actual your actual final aim. And this talk, the focus is on this last part. So we are assuming we are able to divert the control flow, and then we'll see what can we do afterwards. And in particular, we'll see how can we do this last part of the exploitation process in presence of certain countermeasures that I'll present. Because just being able to divert execution is not enough, because, okay, I can, I have control of the program counter, but the question now is, where do I point it to? The where, it's the important thing. And since it's 2015, we cannot, upload a shellcode in our target and just jump there, because operating systems are preventing this kind of stuff. So as you all know, the hackers and exploiters came up with the concept of code reuse attack. So we cannot upload or inject new code, and then what we do? We reuse existing code. So we came up with the famous returning to libc attack, and then all the return-oriented programming, which I hope you are at least a bit familiar with. The problem is that, okay, we are able still to perform our attack, even if we are not able to inject a new shellcode reusing code. But the problem is that, the operating system developers came up with a countermeasure, which is called ASLR, which basically means that it's address space layout randomization, which means that basically the code that you want to reuse, for instance, the system library functions and those kind of functions, are not always in the same position. Their position is not deterministic. So the question again is, okay, I can divert the control flow, the code I want to reuse is there, but where it is. So the typical situation to get around the ASLR is use the functions that are already imported. So the main executable uses some, let's suppose that the main executable uses some functions for instance, the C standard library, like the printf function, which is very common. To be able to use this function, it keeps in memory, in the memory area which is dedicated to the main binary, a reference to this function, which basically holds the address of the printf function. And so the typical way, as I was saying, to bypass ASLR is, okay, let's try to read the address of this printf function, which is actually imported by the main binary. Then, if we have a copy of the C standard library, if you're targeting the C standard library, let's compute the distance between the printf function and another function we want to execute to perform our malicious operations, typically system or execv. We compute this distance, and then if we are able to get from our target the address of printf, we can add the distance to reach execv, and then we know the address of execv, and then we can call execv and perform our attack. This works, but the problem is that, first of all, it requires, you don't just have to be able to divert the control flow, but you also have to be able to leak this piece of information, the address of printf. So you need at least 2 vulnerabilities. You need a memory leak vulnerability, typically. And also you need knowledge about the layout of the library you're targeting. So you basically need the exact copy, not just the version, you need like the exact copy, so the exact build of the library. Which is not always the case. I mean, there are some situations where maybe you don't have access to it. And finally, there's another point which is a bit subtle, is that you need to interact with the attacker. Okay, so it's not a single stage attack. It's not that you just launch your attack and it works. You do your exploitation. You need to communicate back to the attacker. So basically, you read the printf, and then on the attacker side, you compute the new address and you send another stage of the exploit. So it's 2-stage. And this is a problem because maybe if your final target is air-gapped machine, for instance, you can't really communicate. Maybe you have a JPG, you are storing your exploit in a JPG or in a PCAP file or something, which is open on an air-gapped machine, you can't really communicate. So this is a problem. So how can we solve this problem? Let's try to zoom out a bit. Actually, our idea when we came up with these techniques, it's let's try to zoom out a bit. What are we trying to do? Basically, what we're trying to do is to obtain the address of an arbitrary library function. So I have a name, and I want its address. So I'm able to call it. But if you think, well, there is already a part of the operating system doing this job, and it's the dynamic loader. The dynamic loader, basically, the role of the dynamic loader is to take the main binary, or even a library, and see what are the imported functions, for instance, printf, and from the name, from the string printf, obtain its address, where the printf function actually resides in memory, considering ASLR and everything. So let's try to get to know this guy, the dynamic loader. First of all, I'm going to talk about dynamic loading and everything in the context of ELF-based platforms. So ELF, for those who do not know that, stands for Executable and Linking Format, and it's basically the most popular format for Unix-based platforms, so Linux or BSD, like FreeBSD, NetBSD, OpenBSD, they all use ELF, which is a binary format, as I said. And so if we consider an ELF file like an ELF executable, the first way we can see it, we can split it in sections. So it's a file, and it has several parts which are called sections. The most important sections that you usually deal with, and maybe if you've been doing a bit of reverse engineering, are usually the .text. All the sections start with a dot. So the .text section, which holds the executable code, so the actual code, the binary code of the application. Then we have .data, which holds all the writable global data. So let's say the global variables that are writable, they're not just read-only. The read-only ones stay in arrow data, which stands for read-only data. And then we have BSS, which is a section which holds global variables which are not initialized. So for instance, if you, like in C, you write a global array that it's not initialized, it will be 0 initialized and will end up in BSS. Okay? So let's see what's the role of the dynamic loader. Basically, the compiler hides a bit of the complexity of the dynamic loader, because when we see this piece of code, like a very simple hello world program, we see just printf. But what actually the compiler means, it's not a call to the printf in the C standard library, because, as I said, the libraries are positioned in random positions, so you cannot know at compile time where the printf will end up. What actually the compiler does is calling the printf at PLT, which is a trampoline, let's say a small piece of assembly code that we're gonna see. We're gonna explore how it works. This small trampoline is stored in another section, which is called .plt, the so-called procedure linkage table, which is a table composed by this small trampoline, one for each imported function. And basically, let's see how it looks like. So these trampoline are used to support lazy loading. Lazy loading is a feature of the several dynamic loaders, basically most of them, which allows you, when you start the program, instead of resolving all the important functions, getting the real address at the startup of the program, you basically obtain their address the first time you call them. So if there's a function you never call, it's not going to be resolved, and you're saving time, okay? And also the startup of the program, it's faster for the end user. So it works a bit like this. This is pseudocode. It's not, actually, it's an assembly optimized code. What's the trampoline, doesn't look like this. But this is the high-level stuff to make you understand. So if it's the first call, the first time that the trampoline it's being called, the main binary will pass the control flow to the dynamic loader, calling this DL runtime resolve function, which we'll explore in a bit. Otherwise, it will just jump to the cached version of this function. For instance, if this is the trampoline of printf, there will be somewhere in memory, we'll see where, a place where the address of printf is cached. And DL runtime resolve will take care of finding where printf is, storing the address of the printf at that cached printf address, and then also call the function. So DL runtime resolve takes two parameters. The first parameter is just a pointer to a data structure which describes the current ELF object. We'll see more about that later. And the 1, 2, 3 parameter, it's an index in a table. It's an index representing a relocation. So what is a relocation? A relocation is basically a directive for the dynamic loader telling him, so take this symbol. A symbol, it's a concept that represents like a function, for instance, in a library, or maybe a global variable in an external library, so a symbol. Take this symbol, for instance, printf in this case, and write its address at this specific address. In particular, R offset represents where the address of the symbol has to be written, and R info represents it's basically the identifier of the symbol. So relock index, which is the second parameter of DL runtime resolve, it's an index in a table of this relocation. Basically, there is a section called RLPLT section, which is basically an array of relocation data structure, which are called ELF-REL, which are composed of, exactly by R offset and R info. So every info, I said that it's an identifier, but it's actually an index in another table, which is called dynsim, which is an array of symbols, structures, which are actually elfsim, which have a lot of details we are not interested in. The only thing we're really interested in is that there's a field called stname, which is an offset in another table, and this is the last one, I promise, which is called dynstring, which is basically just the concatenation of the name of all the symbols that are imported from a certain binary. So to recap, basically DL runtime resolve takes relock index, which is an index in the RLPLT table, which is a relocation. From the relocation, we pass to the symbol table, and from the symbol table, we pass to the name, which is, in this case, printf. Okay? We'll get back on these things. So, to recap again, DL runtime resolve does three things: finds the symbol and its associated relocation, and finds its address. So if you, from the relocation, you go to the symbol and you go to the name, and from the name, the dynamic loader is able to get its address. It writes that address at the R offset, the address specified in R offset in the relocation, and then it also transfers the execution to that function. So it also calls it. As you might have understand at this point, R offset in this case will point to the address of cached printf address. So R offset tells, okay, right there the address of this function. So next time I'll call the trampoline, I won't have to resolve and do all the trickery to get to resolve the symbol again and just jump straight there. It's sort of an optimization. Okay. So, okay, where does this cached printf address actually is? It's actually in another section which is called GOT-PLT, which is it's mostly known as just the global offset table, which basically holds an entry, which is a pointer, for each imported function. So it's where these cached addresses actually are. So just to recap, we have PLT, which contains all the trampoline which enable lazy loading. We have got PLT, where the cached address of the imported functions are stored, where basically initially they are all uninitialized, and they get initialized lazily from the first time you call that function. We have the table of relocation, which is relocations, which is rel PLT, table of symbols, which is dyn_sim. We have and then we have the table of the symbol names, which is dyn_string, just null-terminated strings concatenated. Okay, so let's try to come up with an attack to this system. So first, some assumptions. Our assumption, as I said, is that we are already able to divert the control flow, and we are also able to run a ROP chain, and we also are able to write arbitrary memory location with this ROP chain. So let's say we have a very small gadget which is able to say, okay, I have this address, I have this value, please write the value at that address. So very simple stuff. What can we do? So if we look at this setting, the idea is, okay, what if I'm able to replace the printf string, for instance, with execv? If I'm able to do so, to replace that string, and I invoke the DL runtime resolve function with the relocation index corresponding to printf, what the loader will do, it will go through relocation symbols, but then in the end, it will end in the dynamic string table, and it won't find printf, but it will find execv. And so it will resolve the address of execv and also invoke that function. So we're basically, in this way, we will be able to invoke any function we want just by name if we are able to write this arbitrary memory location. This slide is called naive approach because this approach actually does not work, because there's no reason why the dynamic string table should be writable. So the dynamic string table, it's not writable because it's like static information that you just write once and you never change. So this attack will not work. Even if we have this gadget, we'll try to write in a non-writable memory location and we just get a segfault. So let's try to work around this. So we've been talking about a lot of different sections, but the dynamic loader actually does not consider sections by their name. It doesn't look up the, PLT, GOT section by name. It uses another section, which is called the dynamic section, which holds basically key value pairs, where the key represents one of the sections it needs, and the value is its actual address. For instance, DT symtab keeps a pointer to the dynamic symbol table. DT strtab, a pointer to the dynamic string table, and so on and so forth. We're not really interested in details here, but the point is that the dynamic loader uses takes the information about the binary, about these sections, from this table. So the nice thing is that .dynamic section is writable. So what we can do is, instead of trying to write directly in the dynamic string table, we can trick the loader into thinking that the dynamic string table is actually somewhere else. And where can we make it point? For instance, we can build a fake string table in the BSS or in any other memory, any other section which is writable by us. BSS, it's typically writable, actually. It's always writable. So basically, we go to the dynamic section and we change the d-value field of the structure, making it point, instead of making it point to dynamic string, we make it point to BSS. So what the dynamic loader will do is, okay, I'll go through relocations, symbols, and then when I'll get to the dynamic string table, instead of going to .dyn_string, I'll go to BSS, where I, as the attacker, I forge a fake string table, which is, instead of printf, as execv. And so basically we are able to perform the attack in the sense of being able to call any function call, any library function, sorry. Okay, but this approach is still quite naive because actually we were not the first people thinking about this. And so the developers of compilers, and in particular of the linkers, develop a protection called relocation read-only, or more shortly like RELROM, which is a binary hardening technique which prevents exactly the attack we just described. Because why is the dynamic section writable? It's simply because there are some entries that we did not describe yet, which have to be initialized at runtime. So it has to be writable when you start your binary, but after you initialize them, you can mark that section as read-only. And that's exactly what the railroad protection tells the dynamic loader to do. And so basically, our previous attack doesn't work anymore. But maybe we can do something else. So we came up with another idea. So far, we played with the .dynamics section. But what can we do if we are able to play a bit with the relock index, the second parameter of the DL runtime resolve? What happens if instead of making it point to an entry in the rel PLT section, making it point to an existing relocation, we put an index which is big enough to go after the end of rel PLT section? Maybe we can trick the loader into going somewhere more interesting. So let's take a look. In particular, can we make the loader think that he has to resolve a relocation which is in a memory area which is writable by us? So not in rel PLT section, but maybe in BSS. So let's see what section do we have after rel PLT. So let's suppose that usually the indexes start from the beginning of the rel PLT section, and if we put an index big enough, we can go through rel PLT, PLT, .text, .dynamic, .plt, and then we can end up in .data and then in .bss. And so, if you are able to trick the loader in going there, and we are able to forge a fake relocation there, we can basically build our own relocation and resolve any library function without touching the dynamic section, which is not writable. So this is an example of the thing. So we put a relock index which is big enough to not to go to rel PLT, but to get into BSS, where we forge a fake relocation, which points to a fake symbol with the same trick. So it's the same trick. So if we start from dynsim, we put an index which is big enough to end up in BSS again. And then the same trick again with the st name, we put an offset in the dynamic string table big enough to end up in BSS again. So basically we are building all the data structure which are needed by the dynamic loader to resolve a library function in the BSS, and using always the same trick of overflowing the section which are supposed to be used. We end up in BSS, and we are able again to call an arbitrary library function bypassing the railroad protection. So here there are just some very simple formula how to compute the addresses that we have to put there, for instance, in relock index and inrinfo and in st name fields to be able to perform this attack. But this is not that simple. This will be quite too good to be true, because actually the binaries around, in particular like in Ubuntu and several other distributions, have a feature which is called symbol versioning, which basically allow you to depend not on any printf function, but on a specific version of printf. For instance, I want printf version from a printf function from the I don't know, glibc 2.22. Okay. This is just an ELF feature, which is actually a GNU extension, but we don't really care. But since it's popular, we have to deal with it. And what's the problem? The problem is that if symbol versioning is enabled, therinfo field is not used just as an index in the symbol table, but it's used also as an index in another table, which is called the GNU version table, which we will not talk about. But the fact is that this index is used for two different things. And so basically we have additional constraints. So what we have to do in this case is either we make both indexes go to the BSS section, and so we can fake also the other data structures which are related to versioning, which we'll not look into, or we can make it point. We can make the version thing point to a 00 somewhere in a memory area where we cannot write. Like if we find like a 00 in text, it's fine. So we just because this just basically disable the versioning. So is it doable? Yes. And it can also be automated. The point is that there are certain situations when this is really, really hard. For instance, in particular with 64-bit binaries using huge pages, huge pages means that you have like memory pages which can be large up to a megabyte. And so basically the read-only part of the binary where we have text, relocation, the relocation table, the dynamic symbol table, the dynamic string table, and all these things, which is the read-only part, it's very far away. It's like 1 megabyte away from the writable page. Okay? And so this huge distance makes it really hard to satisfy the constraint we just saw. And so in this case, it's not doable. The problem is that 64-bit binaries with huge pages and symbol versioning enabled are pretty popular. So we found another solution for this. The idea is, in this case, is not to play around with reloc index, but with current object info. So let's look into current object info. What do we have there? It's basically a pointer to a link map structure. And we have this pointer, it's always stored in a reserved entry in the GOT table, which is the second one. GOT1, it's the second entry of the GOT table. And the nice thing about this data structure is that it has a field called linfo, which it basically keeps a cache of pointers to the entries in the .dynamic section. So the idea is, if we can tamper with this internal data structure of the loader, we can basically go back to the first attack when we were tampering directly with the .dynamic section. And this is actually what happens. So we go to the PLT-GOT section. We go to the second entry, which keeps a pointer to this link map structure. We go to the linfo field, and to in the entry corresponding to DT str tab, which is the pointer to the dynamic entry, keeping itself a pointer to the dynamic string table, we can change this value and make it point to BSS, and we can build a fake dynamic entry, which tricks, again, the dynamic loader into thinking that the dynamic string table is in a memory area that we control. And so we're basically falling back to the first attack we saw. So we are still tampering with the .dynamic table, but indirectly, like corrupting the internal data structure of the dynamic loader. And we can do this reliably and deterministically, because the pointer to this data structure, it's always in the GOT1, in the second entry of the GOT. Okay, then, but still there's an additional protection to this, because Railroad, it comes in two flavors. Partial Railroad, which is the one we just saw, but then there's Full Railroad. Full Railroad, basically, it has all the feature of Partial Railroad, but in addition, it basically completely disables lazy loading. This means that when you start the binary, when you start your program, all the GOT entries are initialized, and the GOT is marked as read-only. So we cannot write in the GOT anymore. And also, since they are not used any longer, the GOT1 entry, which was keeping the pointer to this link map structure, is not initialized. So we lost the pointer to this critical data structure, which helped us to bypass partial railroad. And not only this, we also lose the pointer to DL runtime resolve, which is something I skip over, but we were getting its address from the GOT2 address and the GOT2 entry. And also this entry is not initialized because simply lazy loading is disabled. So with these three things, we don't have a pointer to link map, we don't have a pointer to DL runtime resolve, and we cannot write in the GOT. It seems like we are pretty fine. But DT debugged to the rescue. So there is this feature which is like the typical, debug feature, which is staying there and waiting for someone to abuse that. And here we are. So DT debug is an entry of the .dynamic table, which is used by GDB and other debuggers to be able to break on certain events related to dynamic loading. Like, okay, we have a new library being loaded. You want to break so you can explore this library and see what new symbols you have. So debugging stuff that we don't really care about. But the nice thing is that this dynamic entry doesn't point to a section, but points to another data structure, which is rdebug structure. But this rdebug structure keeps a pointer to link map. So we basically are able, just going through this debugging feature to get back to the previous attack. But it's not that simple, because as we said, we also, so this is the last drawing I'm showing you, I promise. But this is really interesting, because as we said, we don't have pointer, we've found a pointer to link map going through the DT debug dynamic entry, but still we have to be able to find a pointer to DL runtime resolve. So let's see how can we make this. So let's start from this area of the drawing. So in the .dynamic section, we go to DT debug, we follow its value, and we get to R debug. From R debug, we have this field, which is R map, which points to the link map structure that we saw before. So first thing we do, we corrupt the DT_str tab entry, which is the one keeping a pointer to the dynamic entry for the dynamic string, okay? And so we do the thing we just did before. We build a fake dynamic entry, and we build a fake string table, and this is, let's say, usual for now. But the point is that what will the dynamic loader do? Okay, it will go through all this stuff that we craft, and it will resolve execve. Nice. But then, one of the features of DL runtime resolve, it's also storing the address of execve in the GOT. But the GOT has been completely initialized and marked read-only by the dynamic loader because of a full railroad. And so we'll get a seg fault, because we are trying to write in a memory area which is read-only. So we have to also fake another entry of the linfo of the link map data structure, which is JMP rel, which is a pointer, which was the one holding a pointer to relocation table. So we fake also the relocation table. We create a fake relocation, which points to an existing symbol, but as R offset, instead of pointing to the GOT, it's pointing to, like in this case, a memory area just after it, which is writable. So we don't get the seg fault. And so we solved also this problem. Now we have one last problem, which is the address of DL runtime resolve. So we don't have it in GOT2, and so we have to get it somehow. But how can we get it? The trick here is that usually, actually in our survey basically always, only the main binary is protected with full railroad. The libraries are not protected with full railroad. So if we are able to get to the GOT of libraries, we can still get the address of DL runtime resolve. And the nice thing is that the link map structure, it's not just a data structure per se. It's actually part of a linked list of all the link map data structures representing all the loaded ELF objects. So basically what we can do is just we can dereference like the pointer to the next entry in the dynamic in the linked list and get to the link map data structure of just any library, for instance libc or whatever library is being loaded. We go to we get the address of the PLT GOT, and then we go to the third entry, and we get again the address of DL runtime resolve. And basically, we are able to building up all these things together. We are able to bypass also full railroad, which is a pretty cool thing. Okay, okay, this is very interesting, but how can we do that? So we implemented leakless, which is the name of our tool, which implements all these techniques. You just give in the binary, and it tells you which is the best, the approach that is most suitable for this particular binary based on the protection it has enabled, and basically if it's 64-bit with huge pages and those kind of things. And it can produce two different kind of outputs. It can either tell you, okay, do these things. It outputs like a JSON file, which basically instructs you, okay, if you are writing an exploit, write this thing there, and then you'll be able, and then just call DL runtime resolve and everything will work. Or if you provide leakless with the gadgets it needs, and we'll see what kind of gadgets it needs, it can also produce the ROP chain for you directly. So it actually produces the exploit to resolve one or more functions, one after the other, and call them with the appropriate parameter. You can see the code there. It's in GitHub. We just published it. And you can play around. So the gadgets. We talked about gadgets. So basically, we need at most 4 different gadgets, depending on what of the 4 attacks I presented, excluding the first one, which was not working. It was just the first naive approach. Depending on which attack we are dealing with, we have different gadgets that we need. So the first one, the one which was basically just overwriting the .dynamic section, that just needs a memory write gadget. So you give him, you need a gadget, you give him an address, a value to write there, and it writes there. And so basically, all the exploits, all the techniques that we saw need this kind of gadgets. So N stands for no railroad, P stands for partial railroad, H stands for when you have huge pages and all kind of stuff, and F for full railroad. In the other case, we have slightly more sophisticated gadgets. For instance, this one is, if you look at it, it's the one we use to tamper with data structure. So you have a pointer, which is usually a pointer to a data structure. You add an offset, you dereference it, and you write a value there. And this is used for the huge pages attack and for the full railroad. Full railroad has requires two additional gadgets. This one is basically a gadget that we need to store somewhere some data that we took from those, like while we were walking through all those data structures. For instance, the runtime resolve. Basically, you choose a memory area where you want to save this address, and you take it from this data structure at this offset. And in this case, so I initially skipped over this, but for the first three attacks, to call the L runtime resolve, we were using a part of the PLT, which, if you remember, it's where the trampoline were. But in this case, we cannot do that because the L runtime resolve, it's not initialized, and so we also need to be able to write the address of the L runtime resolve directly on the stack. So we need a gadget which allows us to write at an offset on the stack. So we need these four gadgets. And this is also the reason why I'm here, annoying you with 4 different techniques instead of just showing the last one, which is the most powerful one. Because depending on the protection that are enabled, you have different requirements and you need different gadgets, which might be easier or harder, or maybe just take more time to find and implement. So, okay, but after all these things, what loaders are actually vulnerable to this? So in we tested our leakless against the glibc, so the GNU standard library, and against the FreeBSD standard library. But by manual inspection, we deem vulnerable also DietLibc, UCLibc, and ULib, which is embedded. There are C standard libraries for embedded systems, and also OpenBSD and NetBSD. Because basically, they all behave like the same. If you think about it, we're just relying on standard ELF features. And except for minor modifications, maybe for instance, they all cache pointers to the dynamic entries somehow in their internal data structures. They are maybe a bit different, but there's not a real big deal. We say that it's not vulnerable Bionic, which is the C standard library for Android, because as far as I know, it does support only PIE binaries, and Musl, which is an embedded C standard library, because simply it does not have lazy loading. So it's like if you have full railroad all over the place, always. So basically, our tech is worthless. It's a feature. Not having a feature, it's a feature, actually. And FreeBSD loader, I'd say it's kind of not vulnerable because the first and the second attack I presented you, basically the one which was overflowing the relocation table and symbol table and those kind of things, does not work. Because these are the only guys that are actually checking the boundaries, which is like basic things to do, but they are the only ones. But still, the other 2 attacks, they do work. So it's kind of vulnerable and not vulnerable. Okay, so let's recap. What are the advantages of leakless? So first of all, it's single stage. So you don't need a memory leak vulnerability, and you don't require interaction with the victim. We are not sending back to the attacker anything. We just do a single shot exploit, which might work in any situation, and like air gap machine and those kind of things. So like offline attacks, which maybe before were not feasible, are now feasible. It's reliable and portable because it's deterministic. There's nothing left to randomness, or it's very deterministic. And then you do not need a copy of the target library. So if you think about that in the beginning, I told you that you have to compute in the typical situation when you use a memory leak, you have to compute the distance between execv and printf. But to do this, you need a copy of the library, which is not always the case. In this case, we do not care about the layout of the library. We just abuse the dynamic loader, which does it in the proper way. And since it relies on just standard ELF feature, in most cases it's very portable and it's easy to port, for instance, to NetBSD, OpenBSD, and so forth. Except its link map layout of the data structure, but as I told you, are really minor fixes to the exploit. It's short because if you want something with the same characteristic I just mentioned, like reliability and being deterministic, you will need to basically re-implement what the dynamic loader is doing. So implement like in PureRop, going through all the relocation symbols and those kind of things, which is very complex. And it's also, it gets very long because it's not just say, okay, dynamic loader, do this for me. You have to do it by yourself. And also, the advantage of leakless is that once you set up all the data structures, if you want to make multiple calls to different library functions, you just need to, after you did the first one, you just need to change the name of the function you want to call and just call again DL runtime resolve. Instead, if you want to implement the dynamic loader, you have to do again all the process. And so it's a cost that is not negligible. And shorter ROP chains mean higher feasibility. Sometimes buffers are small and you have limits. And if you don't want to interact again, you cannot read. If you want to do it single stage, being short is important. We also say that it's stealthy because basically we are not, the typical criticism one could make to such an attack is that, okay, but why don't you just do this with syscalls? Okay? Because first of all, syscall might not be available. You might not have them in the binary, like even in misaligned. But it's also more invasive. Because for instance, you can always do, if you can do syscall, you can basically do everything you want. But you might have an intrusion detection system and also spawning a new process, for instance, if you want to do execv, it's kind of invasive. And here is an example of a thing we came up with. It's a pseudocode for using pidgin functions. Pidgin is IAM client. And so what we're doing here is we're taking the pointer to the proxy object of pidgin, and we are setting, so the attack we want to carry on is like, okay, set a proxy so I can intercept the instant messaging traffic for this user. So what we do is we take the global object for proxy, we send a proxy which is our server, the port, the type, and then we connect and disconnect the user. Sure, you can do this also with syscall somehow, but reusing a program functionality, it's much easier and it's less intrusive, and it's also easier. And also it's automated. And by this meaning that our tool basically does almost everything except finding the gadgets. But maybe in the future we can integrate it with some automated gadget finding tool. So, countermeasures, well, the most obvious countermeasure is enabling PIE, so randomizing also the position of the main binary, okay? This is an actual solution, but actually in our survey there are like PIE is not being deployed a lot. The distribution basically use it on binaries they deem critical. I don't know why they don't deploy it on all the binaries. It doesn't make sense to me, but this is a possible solution. Also, DT debug, why should it be there? Just remove it, or maybe enable it only if there is like an exported variable if you want, like an environment variable. If you want to do debug, then you can enable it. Or you can try to make the dynamic loader data structure read-only, so if you try to tamper with them, you get a crash. Or just validate the input is also a very good countermeasure. But the key point is that this kind of core components of the operating system should be retold with security in mind, because basically all the libraries we inspected were just trusting user input. And since they are all over the place, it's very dangerous, because if you're able to attack them, you are able to obtain something that is very portable and it's all over the place. So also ELF maybe should be redesigned a bit with security in mind from the beginning. And this last thing, I want to thank all the other people who worked with me in this, like Amat, which is here, and Jan, which is not here, and Giovanni and Christopher at UCSB, which allowed me to be here. And that's basically all. Maybe I have a second to do a very short, so just to show you some code. So this is, I'm just going, we tried to implement, to attack a real binary, because we have a small test suite in leakless, but we also want to do something real. So we took a CEV in Wireshark, just a very basic stack overflow, a stack buffer overflow. And we tried to generate an exploit with leakless, just providing it with the gadgets. Oh, just a small demo. We launch it. This is just an error because I'm running Wireshark as root. Don't do that. It's a very bad idea. We launch it passing a pickup, which I generated, and I got a shell. So it's pretty easy. Yeah. Shell are always good. Yeah, and then we have the same with partial rev, but it's the same experience for you, so just trust me. So the last thing, this is the part, leakless has been implemented in Python, and this is the code that you need to write if you want to provide gadgets to them to leakless. And it's 200 lines of code, but most of them it's just boilerplate that could be factorized out. And it's basically just take the gadgets and mix them together so they can be reused by let's say the part of leakless which is agnostic from the binary. And last thing is, I just wanted to show you the JSON output. Let me see. So this .exploit.py, it's basically the leakless script. We pass it the Wireshark binary, and we ask him to produce the exploit in JSON format using the LD corrupt method, which is the second one I presented. And what it does, it basically gives us some instructions like, okay, write these things at this address, and so if you don't want the rob chain to be generated automatically for it because maybe you have some complicated setting, it can just give you the instruction to perform the attack. With this, I'm done, and thank you for your attention.